everyone, and welcome again. So we'll be continuing our study of the energy module, and in today's lesson we'll be talking about energy profiles and energy profile diagrams. Okay, so I'm sure you've all seen lightning at some point, maybe not as impressively as this, but lightning is just a form of energy. It's electrical energy, and so in this we're going to study how energy and heat and light are all sort of interrelated in a chemical sense. Okay? So before we study anything to do with chemical reactions and energy, we need to study a concept called enthalpy. All right? And enthalpy is a very subtly different property to energy. Okay? So a lot of people confuse these two things because they do sound alike, but enthalpy refers to the heat content of a system. Okay? So energy can be all sorts of things, but enthalpy relates more specifically just to the heat content of a system. But it can also be thought of as the total energy of a system. Okay? So the total energy within a system is called the enthalpy, right? Now that may be confusing, but if you go on to study university, you'll think thermodynamics in university, you'll see things like entropy, exergy, and all sorts of things that sound all the same and all kind of mean slightly different things. So, and the reason why we do this is because in this little lumped body here, we don't really know what shape this is. We look at the energy coming in terms of its enthalpy, and we look at the energy coming out in terms of its enthalpy. So H in and H out. So enthalpy is given the symbol H. And then we can see how much energy or enthalpy is consumed in a reaction or produced in a reaction. Okay? And it's in the units of joules, but joules is what we'll use in chemistry, HSC chemistry, but in sort of university thermodynamics and chemistry we'll tend to use kilojoules because it's a kind of more convenient unit to deal with. But we're not really so concerned with enthalpy of one state. We want to just know the change in enthalpy. So after a reaction, what is the change in enthalpy? That's what we're interested in. And that's given the symbol delta H. So delta is change in, just like in maths, and H is enthalpy, of course, that I just mentioned. So basically the reason why enthalpy is used rather than energy is because it accounts for all of the components of the system. Okay? So there could be energy put into the system because of pressure, like some kind of piston pushing down on it. There could be energy taken out of the system by something evaporating, which is called the latent heat of vaporization. There could be energy taken in by just the temperature going up of a chemical. So all of these different energies that are kind of inputted and outputted of the system, like just sort of taken in and taken out of the system, can all be accounted for with enthalpy. And so that's why it's convenient for us, because we just want to lump all the energies sort of together and then say, this is the final number. It's much easier to deal with. Okay? So that's why we use it. And personally, I think it's a very, very useful unit, a very useful property. But it just does get a bit confusing when people don't define it very well. Okay? So then, now that we've covered the enthalpy, or H, we can talk about energy profile diagrams. And these are two energy profile diagrams. And so one way to consider chemical reactions is to look at the enthalpy of the products and the enthalpy of the reactants. So when we have a reaction, we can just say, well, what is the enthalpy of the products? What is the enthalpy of the reactants? And then what happens in between? Okay? So when we do that, we tend to graph it and we call it an energy profile diagram. And so reactants are always on the left and products are always on the right. Just like in a chemical equation, the reactants are always on the left and the products are always on the right, okay? Unless it's an equilibrium reaction, then it's a bit different. So interpreting the diagram, remembering that energy always has to be conserved, right? So for instance, let's look at this diagram. If enthalpy of the reactants is here, and enthalpy of the products is here, there's a big enthalpy difference, right? Now, that energy has to go somewhere. So you can't just disappear. That's just not physically how it works. So that could be given off as heat or light or sound or something, right? Now in this case, the enthalpy of the reactants is very low and the enthalpy of the products is very high. Now the question then becomes, well, where did that energy suddenly come from? Well, we had to put in energy, if you look at it. So we went from low to high, so energy must have been put into the system so that we could change the enthalpy of the reactants and it would go up and become the enthalpy of the products. Okay? So that's what we see when we see an energy profile diagram. Okay? And it's basically just an expression of conservation of energy. So from this, as I just kind of pointed out, and you should maybe have clicked onto it already, you can determine whether a reaction is endothermic or exothermic. So because the energy is released here, because the enthalpy of the products is high, the enthalpy of the reactants is high, and the enthalpy of the products is low, and energy is released because that energy had to go somewhere, then we have an exothermic reaction because we get heat and light. In this case, the enthalpy of the reactants is low and the enthalpy of the products is very high. So the products have more energy than the reactants, which means that we had to put in energy to get them to go that high, to get that extra energy. So it must have been endothermic. Okay, so just from the shape of these diagrams, you can see if it's exothermic or endothermic. Okay. Now, to determine the change in enthalpy, delta H, this guy, we take delta H to be the enthalpy of the products minus the enthalpy of the reactants. Okay, very, very simple equation. Products enthalpy minus reactant enthalpy, and that's delta H. Now that's why in an exothermic process, delta H is always negative, because you can see here that the enthalpy of this product is very small, but the enthalpy of this reactant is very big. So a small number minus a big number will be a negative number. Okay? It's like saying 40, it's like 2 minus 40 is negative 38. So that's why in an exothermic reaction, delta H is always less than 0. Now in an exothermic reaction, so if the enthalpy of the reactants is greater than the enthalpy of the products, then energy must have been released from the system. Okay? Because the energy is high there and low here. So energy had to go out of the system. Now that's what we call an exothermic reaction. So energy in the reactants cannot just disappear, so it is released as heat and light. Okay, so if we look at it here, we put in a little bit of heat, it climbs over the activation energy, and then falls down, and all these waves come out. That's just light and heat. Okay, so you can see they're different, they've bonded differently, and the release of energy is there. Okay, so one more time, you can see all of this energy coming out, because this energy is much bigger than this energy. So we had to get rid of some energy somewhere. And that's how it does it, by releasing heat and light. Okay? Now for an endothermic process, if the enthalpy of the reactants is less than the products, energy must have been taken in by the system. Okay? So if the enthalpy of the reactants is low and the enthalpy of the products is very high, obviously there's an imbalance of energy, so energy had to be put into the system to make up that difference. Okay? And thus it's what we call an endothermic reaction. So the energy of the products cannot be greater than the energy of the reactants without an external source of energy. So you can't just have this energy suddenly turning into this and nothing else. That doesn't make sense, because energy can't be created. It has to come from somewhere. Okay? So you can see you heat it up, it goes up to the top and then settles down here, and then so we had to input that heat at the bottom. Okay? So that covers this lesson on the energy profile diagram. So hopefully you've been able to see how exothermic and endothermic reactions interact in terms of enthalpy, and you've also learned about what enthalpy actually is. I haven't really defined it very well or very rigorously because it's not necessary. But what you need to know is that it's a very useful measure of energy in a system. Okay? So move on to the question segment, and hopefully we'll see how all of this fits in a physical context. So question 6. Why is enthalpy a useful measure of energy to chemists? So why would we want to use enthalpy when we have energy, we have entropy, we have exergy, we've got work, heat, all these words that all kind of mean similar things. Why do we want to use enthalpy? Well, the reasons are here. So it measures the total energy of a system, as I mentioned in the class. Now, this is the key point. This energy can be in a variety of forms. So you've got chemical energy. So we can talk about enthalpy in terms of chemical energy, and that's what's called the enthalpy of formation. It could be energy taken up by changes of state. So in other words, energy, the enthalpy of vaporization or the enthalpy of condensation. So the enthalpy created by or absorbed when something changes state, from solid to liquid or liquid to gas or solid to gas or any sort of those things. And energy can also come from pressure. So when you put pressure on a system, you're putting energy into that system. So this enthalpy can account for all of these different things, all in the one parameter, which is called enthalpy. So all of these different forms of energy can be collected by the enthalpy term, which can then be used in energy calculations. So we can collect all this energy and say, this is enthalpy. And then we can collect all the energy at another state and say that's enthalpy 2. And then we can just do the division or do the subtraction, and we can work out delta H really easily. And that's why we use enthalpy, because it collects all sorts of energy terms together. So in an exothermic reaction, what does the activation energy physically represent? So in an exothermic reaction, what is the activation energy? Well, the activation energy represents the energy required to break enough bonds such that new bonds can form, which can generate energy to produce a self-sustaining process. Yeah, that's quite a bulky sentence. But essentially, it represents the energy required to break bonds. So we've got to break the bonds in a chemical so that new bonds can form. So once those bonds are broken, those atoms will form new bonds, which will then release energy. So when they form new bonds, they will release more energy. And that energy can go and break more bonds and sustain this reaction process. Okay? So the energy required to begin the reaction by breaking the initial bonds is a sort of shorter way of saying that. Okay? But this is more of a physical representation, or a step-by-step method. Question 8. The endothermic energy profile diagram shows the products with less energy than the peak activation energy. So why does the energy of the products decrease? That's an interesting question. So if you look at the energy profile diagram of an endothermic reaction, you've got a low energy or low enthalpy at the start. Then it goes up, and there's a hump, and then it falls back down. Okay, so this is your reactants, and this is your products. But then there's this weird hump in the middle where you had to put in all this energy till it got to here, and then it falls back down. So why does it do that? And that's what the question is asking. Cool. So when the chemicals reach the peak of the energy profile, with that hump there, they break down into their component atoms. Okay, so once they're at that peak, they're all breaking down into their whatever atoms that make them up. This means that the atoms are free to move, and their corresponding energies are very, very high. Okay, so because they're free, their energies can be really, really high, because their reactivity is really high and they can move around a lot. However, once they bond together, the products to form the products, their energy is reduced as they are less motive. Also, when they bond, they also release some energy. Maybe not much, but they release a little bit, because that's what happens when you form new bonds. You always release energy. So the energy of that must come down then, because when you form new bonds, you have to release some of that energy. So their total enthalpy is less than that at the peak of activation energy, because they released some of that energy and became less motive. Okay? So that's why there's that hump, because they do have to decrease their enthalpy a little bit, because they're emitting some energy back to the environment. Okay? So water and carbon dioxide are both notoriously difficult to change through chemical processes. What does this say about the enthalpy of these chemicals? Okay? So carbon dioxide, we spoke about in the last lesson, is really hard to change. Water, we can change to hydrogen and oxygen, but only if we put in a lot of electricity. which is why the hydrogen economy and all those hydrogen-powered cars and things like that, maybe not so close, or maybe not a technology that we'll see in the near future. So what does that tell us about the enthalpy of these chemicals? Would it be very high or would it be very low? So the enthalpy of these, or energy, so the enthalpy or energy of these chemicals is really low, okay? These low energy substances are very stable and thus require a large amount of energy to be converted to other forms. So if you think about hydrogen and oxygen, if you burn them, you get a lot of energy out, okay? But if you make them from water, then the question becomes, well, where that water had to have energy put into it because it's a very low energy chemical. So you had to put in a lot of energy to get it to hydrogen and oxygen, which means that you take a lot of energy just to change its form. So in other words, water has a very low energy at the start. Because their enthalpy is so low, often these chemicals will participate in endothermic reactions. So in general, water will participate in endothermic reactions, and so will carbon dioxide. Okay. So question 10, what information does an energy profile diagram show, or show you? Well, here are two energy profile diagrams. Well, one thing it shows you is the enthalpy of the products and the enthalpy of the reactants. Even if it doesn't tell you the exact values, it at least gives you a comparative difference in these two. It can also show you the change in enthalpy. Okay. It can show you the relative size of the activation energy compared to the delta H, or the enthalpy of the products or reactants. So it shows you the activation energy, EA. And it also shows you the reaction path. So if it goes up to the top and then down, or if it goes in this way. So it shows you the direction the reaction occurs in. Okay. So that concludes today's lesson on energy profile diagrams. We looked at what an energy profile diagram is, and also the concept of enthalpy, which is a little bit new to you guys. But it's just similar to energy. Just talk about it as, the whole energy of the system. And we also talked about endothermic and exothermic reactions with regard to energy profile diagrams and enthalpy. So in the next lesson, we'll be talking more about practical applications of energy, in particular engines. So for those who are interested in cars, the next lesson will be about gasoline or petrol cars and diesel cars as well. So look forward to seeing you at our next lesson.